Okay, so hopefully, yeah, everyone can hear me. You can see the slide. So what we're going to talk about today, well, almost entirely today, is how to exploit the fact that modern processors or modern supercomputers are built out of multiple shared memory nodes. Now, it's important to note that the MPI ignores that completely. Well, at least previously when it was first written, it did. The MPI model is you run a lot of processes which communicate with each other, and that's the model. And then, of course, at runtime, in practice, those processes, operating system processes, are mapped onto physical hardware processing cores. And in the original, when MPI was designed, that would have meant single core processors. So the target platform that MPI was written for or designed around was really a bunch of single core processors connected by some network. Now, of course, that's not to stop you running MPI on your laptop, where you have nowadays multiple cores on the same computer, but the model for MPI is very much driven by single core processors connected over a network. And then, of course, now we have massively multi-core processors. So we have, on ARCHER2, we have 128. And so the question is, you know, how do you exploit that, or should MPI be aware of that? And MPI is now aware of that. But the programming model, which was specifically designed for shared memory multi-core processors, is OpenMP. It's actually very unfortunate that OpenMP, which stands, I think, for Open Multiprocessing, sounds a bit like OpenMPI. OpenMP and OpenMPI have nothing to do with each other whatsoever. That's a very unfortunate naming convention. MPI is an open source implementation of MPI, and they shouldn't have called it OpenMPI, because OpenMP, which is a bunch of shared memory directives, compiler directives for doing shared memory threaded programming, came around first. But anyway, so there's a number of ways of exploiting the shared memory nature of the hardware. And the obvious one is to combine MPI and OpenMP. You have a model which can cope with distributed memory computers, and you have a model which is designed for shared memory computers. Why not put them together? That's been something which people have been looking at for almost 20 years. And MPI now has some support for that. That's what the first two lectures of the morning is going to be about. And the afternoon, I'm going to talk about MPI's more recent inbuilt model, pure MPI model, for exploiting the fact that two processes might actually be on the same physical computer, the same shared memory node. So this is my long lecture, but I'm going to give it in two parts, so don't worry. So, I mean, I'm actually going to spend this first lecture is really going to talk about the motivation, the advantages, and the problems. We won't actually get onto actual syntax or code till the next lecture. And that's because I think it is very important to go into this with your eyes open. A lot of people, well, not so much now, but, you know, a few years ago, a decade, when a lot of people jumped in and spent a lot of effort converting their programs from being pure MPI to MPI plus OpenMP, and then didn't see any benefit. And so you really need to think quite hard about whether it's worth doing, because it is quite a major update to your program. So I'll talk about the motivation, a lot of which I've just talked about anyway, and the advantages and the potential problems. So as we said here, with the ubiquity of multi-core chips, almost all current CPU systems are clustered architectures. Distributed memory systems, we know, consist of a shared memory multiprocessor, SMP. So the important part is you have a single address space within each node. What that means is, in principle, you could have shared arrays. You know, that's the basic point, that you can have a single array that can be accessed by multiple, in OpenMP, multiple threads. And we'll see later you can do it with multiple processors, and that is because, you know, you have a lot of CPU cores physically connected, directly connected to the same memory, or actually more importantly, a bunch of CPU cores under the control of one operating system. So in fact, the really important thing, which I haven't got here, is that not only do you have lots of shared memory multi-core computers connected together, but each multi-core computer like your laptop, is controlled by a single instance of the operating system. So if you have 1,000 nodes, like we have on ARCHER2, you have 1,000 copies of Linux. A copy of Linux is in charge of 128 CPU cores, and so it can give all those CPU cores access to the same section of memory directly, and the access is through the hardware. So you have a single address space with each node, but separate nodes have separate address spaces, and that's why we need to use message. We'll always need to use message passing MPI to communicate between nodes. Again, actually, because you're communicating between operating systems, different operating systems, or different instances of the operating system. So how should we program such a machine? We could use MPI across the whole system, and actually that works remarkably well for so maybe not obvious reasons that we could discuss, but MPI does work remarkably well on a node. You can't in general use OpenMP or threads across the whole system because it requires a single address space. So I mean, MPI uses processes which are completely independent of each other, and unless you do clever tricks, cannot share memory with each other. OpenMP uses threads, and the whole point about threads is they're designed to share memory with each other. You know, the idea about threads is you have multiple tasks, little programs operating on the same data. Okay? So for example, my browser window here is a single piece of memory, and it's got lots of threads operating on it. It's got things updating the, updating the tabs and updating the animations and presumably checking for notification, all kinds of things. And so threads are designed to operate on the same pieces of memory, whereas processes are designed to have separate pieces of memory. There are ways you can try and get threads to work across a whole system, but it doesn't really work. So the obvious thing, which occurred to people over 20 years ago, could we use OpenMP and threads within a node and MPI between nodes? Is there any advantage to this? So in general, experience shows that MPI and OpenMP does not improve performance where MPI is scaling well. So if you have a program which is performing relatively well, scalability wise, parallel efficiency wise in pure MPI, there's nothing magic that OpenMP is going to give you. It's not a panacea. However, the benefits come when scalability of your MPI program runs out, either in time, i.e. runtime, or memory, and we'll see that you can actually use OpenMP to share memory. So where people have had successes are where their MPI program has run out of steam, and by adding OpenMP, they've been able to extend the scalability to larger core counts. And in particular, so this is sort of a typical performance we'd expect. And this is why actually, developing hybrid MPI OpenMP codes is quite tough, because of course you develop codes on small numbers of cores, but you only, to see the benefit, you need to run on large numbers. So your pure MPI code might go like this and top out here. And by adding MPI plus OpenMP, you probably take a hit, or wouldn't expect any benefit at small numbers of cores, but at large numbers of cores, you would expect to extend the inevitable turnover to some higher number. And so that's the kind of thing you might see. So it's really there for extreme scalability, basically. But of course, we are in that regime now, because modern computers will have, and the final ARCHER2 system will have 750,000 CPU cores, which is really quite astonishing. So the potential advantages of MPI plus OpenMP are reducing memory usage, exploiting additional levels of parallelism, reducing load imbalance, and I mentioned briefly on Wednesday that load imbalance was quite tough to address in MPI, and to reduce communication costs. So reducing memory usage. Some MPI codes have a replicated data structure, where you have some data structure, some lookup table, and all processes have a copy of the entire data structure. Now, that could be some table of just the data, or some big lookup table. In most scientific and technical codes, that's not particularly common to have that, but it does happen. But you may say, well, I don't have any replicated data in my program. Well, you probably do, because the classical approach to domain decomposition is effectively that the Halo data is replicated. You have a copy of, in your Halo, of your neighbor's boundary data. So, and that you may think, well, Halo is just a boundary region. It's not that big, but actually it can take up a surprising amount of memory. Also, MPI internal message buffers can consume significant amounts of memory. If I run MPI in the naive way, well, the standard way on ARCHER2, I have 128 copies of the MPI library per node. The MPI library itself uses memory. That could consume significant amounts of memory. And pure MPI code needs 1 copy per process or core, but a mixed code, a hybrid MPI+OpenMP, would only require 1 copy per node. And the data structure can be shared by multiple threads within a process. And that means that you also don't need any buffers for intranode messages. They're no longer required, because you don't need to send data on a node it's not accessible. And so, you know, the feeling is this will become increasingly important. And that because the memory per core is not likely to increase. I mean, on ARCHER2, we have, I think we have 2 GB per core. I think that is correct. I think we have 256 GB of memory across 128 cores. On Archer, we had 64 GB or more across 24. So we had 3. So it's gone down a bit. Thanks, Kevin. 2 GB per core standard, where it was more like 3 on Archer. And that is, you know, that is not going to get bigger. You know, we're going to get more. Memory is expensive, and you know, expensive in both. Definitely cost, I believe, in power as well, in terms of running memory, but we're not going to get more memory per core. So, you know, in the early days, we had small numbers of cores and small amounts of memory, and then memory got spectacularly cheap. And Bill Gates' statement that no one will ever need more than 640K of memory seems a bit crazy, but that's the kind of, you know, a megabyte of memory seemed like a huge amount in the 90s. And now then we have huge amounts of memory, but that memory is on a shared memory node. So your computer has 256 gigabytes of memory. That sounds fantastic, but you stuck 128 cores on it. So each MPI process only has a couple of gigabytes. And so I don't actually know how much of that 2 gigabytes is usable on ARCHER2. I don't know how much is taken up by stuff. I've not measured that. That would be an interesting thing to do. When I say the MPI library takes up space, it's the storage for the MPI library. The code for the MPI library is shared. That's what a shared library is. I believe. Oh, is it? I believe it will be. Wouldn't it be on Archer actually? Okay, I'll shut up. I'm straying into operating system areas that I don't know much about. But anyway, reducing memory usage is potentially a big win. And why is that a problem? Well, you know, if you require 4 gigabytes per process, that means you can only run 64 processes on an ARCHER2 node. So you have to undersubscribe the processors. You're wasting resources, and so that could limit. But you still have to pay for the whole node. You know, we don't care. So that actually is if you are having to run fewer processes than physical cores purely because of memory limitations, then these techniques can be very good. So again, you might not believe domain size that your halos can be significant, but using more process, again, we're always thinking here going to the future as we run on big systems. As we use more processes, the domain size per processor gets smaller, unless you can genuinely weak scale, and people don't. And people run bigger problems on larger systems, but we don't typically tend to. We're typically looking for strong scaling. We want to run a particular problem in a faster time. So the Halo data decreases, the local domain size decreases, but it occupies a significant fraction more of the storage. And even for a single depth Halo, if the local domains, and we've got a 3D code, okay. So if we had double depth Halos, or we're using more than 3 dimensions. then this is going to get even worse. But if we have a 50 cubed local domain size, we have 125,000 points, but the actual array we declare is extended by 1 in each, so it's 52 cubed. So we end up with 11% of data in halos. Even that doesn't sound too bad, but if we go up to 10 cubed here, okay, then we're actually looking at almost half our data is in the halos, and that's starting to get quite significant. So and so that is something to worry about potentially. So you may say, I don't have any replicated data in my code, but you probably do. The other thing you could do is exploit additional levels of parallelism. Parallelizing an MPI is very manual. You look at your problem, and you might have some weather forecasting or meteorology code, and so what you've done is you have parallelized across the domain. So each processor, each MPI process gets a physical a region of the UK to work out the weather on. Okay, one processor might be working on the weather in be working on the weather in Edinburgh, above Edinburgh, for example. However, there could be additional lower levels of parallelism within that. Simulating the weather across the Edinburgh region, there could be ways of parallelizing all kinds of processes that are going on, but could be very difficult to do in MPI because the lower levels of parallelism could often be harder to load balance or have more irregular runtime determined communication path. That's actually very true of weather, because it's very you might have a very complicated calculation which is used to predict rainfall. But if there's no rain clouds, then there's nothing to do. So anyway, so maybe, and also someone may have given you an MPI code where, the original design decision was this will be parallelized across the physical domain. And now you say, well, to go to larger process counts, we need to introduce additional parallelism, but that's not possible in MPI. It's often much easier to exploit parallelism using OpenMP threads. That's because OpenMP, first of all, OpenMP in the language has ways of parallelizing and load balancing dynamically loops, which is very hard to do in MPI. So that's built into the library. And the main reason is because you can have shared arrays, okay? On each iteration 1, you could say, threads, the first 64 cores do this calculation, the second 64 do that calculation. Then you realize that this calculation takes longer than that one. So you say, well, I want 96 cores to do that part and only 32 to do that. As I keep saying, in MPI, to do that would require physically communicating the data with messages between the different processes, which is going to potentially counteract any improvements. But in threaded programming, all these threads can see all the data. My model for threads actually is a lot of people in an office with a shared whiteboard. You have a big shared whiteboard, which is your memory. There's 8 of you in a shared office, and you can all read and write to this shared memory. That is the shared whiteboard. So we can also take an incremental approach to adding OpenMP. That has pros and cons. With OpenMP, you can apply it on a loop-by-loop level. Now, obviously, the OpenMP parallelism can't go beyond a node, but this may be enough. I mean, it's very. I mean, I'm not a real hardware person, but it is quite astonishing. We think that computers are getting bigger and bigger and bigger and bigger and bigger, and they are. But ARCHER2 is going to be 10 times more powerful, at least, than Archer, but it has about the same number of nodes, 5,000 or 6,000 nodes. The increase comes in a factor of 5 or 6 increase in CPU cores per node. So actually, the number of nodes, a few thousand nodes, has been fairly commonplace in HPC systems for a decade or so. The increase in power is coming from multi-core nodes and, of course, GPUs, which are another thing. So reducing load imbalance, as I said here, just reiterating this, load balance with an MPI process can be hard. You need to transfer the data as well as the work. And also it's often very difficult to do globally. And so often you have to basically restrict to transferring load between neighbors. A lot of load balancing algorithms in MPI are kind of diffusive. You say, I've got too much work. I don't know how much work most people have got, but I know how much work my neighbors have got. So I'll give off some work to my neighbors, and then they might offload to those neighbors. So it's kind of diffuse. Load balancing between tasks is much easier between threads. We only need to transfer tasks, not data. Overheads are lower, and it's easy to have a global view. You can have a complete view of the workload of all the tasks, all the threads on a node. Actually, a modern OpenMP also has a tasking model. The tasks which allow you to dynamically assign in a kind of a task farm way, dynamically assign work to the next free thread is again built into OpenMP. So for application with load balance, keeping the number of MPI processes small can be an advantage. If your MPI load balancing algorithm isn't particularly good, it's much easier to load balance across 1,000 nodes than across 128,000 cores. And so you would do a reasonable job of load balancing your calculation across 1,000 nodes, then use OpenMP to load balance within the 128 CPU cores on the node. Reducing communication costs. Naturally, to suppose communicating data inside a node is faster between OpenMP threads than between MPI processes. Because there's no copying into buffers. Again, if two OpenMP threads want to communicate data, one says to the other, there it is, it's just there on the whiteboard. In MPI, you have to package it up into a message, send it, and unpackage it at the other end. There are some caveats. The main point, though, is that this is rarely the bottleneck in MPI codes. Any calculation is limited by its slowest part, and so when you have a large MPI program, you have a lot of messages going between processes on the same node, which are quick. So they're effectively for free. So speeding them up doesn't help you. It's the messages which go between nodes which are the killer, and that can be an issue. So in some cases, MPI codes communicate more data than is needed, and I've got an example here. If you have irregular data dependencies, you don't know what data depends on which data, then you basically have to send everything just in case. If you use OpenMP, you can kind of help. You can mitigate that. And so, there's an example coming. Okay, sorry. The other cases where it can help is in collective communication. In some circuits, like collective communication can be improved by using OpenMP plus MPI. So the reason is, if you have, let's think of an all-to-all. An all-to-all is a collective where every process sends data to every other process. It's typically used to implement array matrix transposes. If you're running on 100 ARCHER2 nodes, that means you have over 12,000 processes, each communicating with each other. So that means the network has 12,000 messages going on it. Okay, with 100 nodes, have 12,800 CPU cores. And so the network may get flooded with a large number of small messages. If you only had one MPI process per node, you'd only have 100 messages going between each set of processes. And now you would hope that the hardware and the MPI implementation would cope with this. You would hope the MPI implementation would actually aggregate data on a node-by-node basis, send it off, and disaggregate it at the end. But for things like all-to-all V, which is a more unstructured and difficult there's a lot more parameters than all-to-all V. Each process can send and receive different amounts of data. It can be hard to do. And so the MPI library can find it very different. So another reason why MPI plus OpenMP can be useful is that you end up sending a small number of large messages rather than a large number of small messages. And that, of course, helps because a lot of small messages are dominated by latency. So the example here is European Centre for Medium Range Weather Forecasting. They have a weather forecasting code called the Integrated Forecast System, I think, IFS stands for. They have something called semi-Lagrangian advection, but I mean, it's kind of obvious. I'm not a weather forecaster. It's kind of obvious that data is transferred in the direction of the wind. Okay? You know, if I'm a region of the UK, okay, I need to give data to the person who's upwind from me and get data on the person who's downwind from me. But that means that the communications is data dependent. Depending on which way the wind is blowing, you have to communicate different data in different directions, and that's very difficult to do in MPI. MPI is very bad. MPI's model is very static communications. It's very hard to not send a message to somebody, because unless they know you're not going to send them a message, they'll issue a receive and everything deadlocks. So their MPI solution was a pragmatic one: communicate all the data to neighboring processes that could possibly be needed. However, in their MPI+OpenMP solution, at least within a node, you have access to all the data. You only need to read the data from other threads' grid points if it's actually required. So a significant reduction in communication costs, a significant reduction in memory usage. And the reason is that the IFS example is sort of saying, if this is the process decomposition, okay, if the wind is blowing in that direction, first of all, they need halos. They need very deep halos, and halos of depth 2. So if the wind is strong enough, when a single time step, you might need data in this example from 2 grid points away. But you actually only need data from these guys here, because of course you don't need data from these guys if the wind is blowing in a different direction. And so you only need to transfer this data. That is difficult to do in MPI. But in but if we do a decomposition where we have a domain per node, we win because we get that surface to volume effect that we saw in the halo. So the halos take up a lot less storage. We transfer a small number of large messages, not a large number of small messages, and everything just works much better. Now, the reason they were able to do this, we can discuss this later. We've looked at the practicalities. Is their design decision they've taken. They have quite an elegant design at a high level for their code, allowed them to very easily say, I don't want this region to be controlled by a single process. I want this whole region here to be controlled by a process, and each of these regions to be managed by threads. That again, I don't know if it was by luck or by design, but their code design allowed that to be done in a very elegant way. That may not be true for your code. What are the problems with them? So, are there any questions about that? Just to say, you know, I've given you the sort of party line here, which is the reason why MPI+OpenMP, or at least exploiting shared memory, might be a good thing to do. So, oh, excuse me, I tried to eat something. Just been apologies. So David has found a need to underpopulate, actually not to memory cache, but possibly ban some of the resource contention. I guess Sheb may not help with that. Well, so I think I don't know if I think I've worked with you on some of these problems before. Yes, so if it's the code I'm thinking about, and I can't remember what it was called, you have a kind of an all-to-all pattern. Is that correct, David? Is that sort of the pattern, the part of the code which is giving you performance problems is a sort of a global communication all-to-all? Or are you talking about a different code here? But if it is that, if it's bandwidth contention, it's not going to happen. It's not going to help underpopulation. But it might. You could be the other difficulty that modern computers have is that the network. When we did the ping pong example, we got very good results, really lovely high bandwidths. But you have to remember that we have on ARCHER2 I think we have 2 network connections per node, but we have a fixed number of network connections per node. And so if you have every CPU core running MPI, then you have 128 CPU cores sending data on and off the node, and that can cause, as you say, resource contention, often more like what's the word I'm looking for? Like a traffic jam, a congestion. Yeah. So the network interface may not be able to cope with that number of small messages, and so again, it's possible that if your issue is basically overloading the network with too many messages, when I say too many, I mean, I'm not blaming you. I'm saying more messages that it can cope with. That would be solved by underpopulation, but shared memory might help you, because that would then you would then be able to run on all the cores, and you would be sending the same number of messages. Now those messages would be bigger. So you're absolutely right. It is critical here if it's bandwidth or latency that's your problem. If it's bandwidth, then you're absolutely right. Then there's nothing you can do. You've saturated the node. Not nothing you can do, but it's difficult. But if it is contention in terms of the number of messages, so congestion, then that might help. I don't know if that's a reasonable. I mean, ARCHER2 is a new network, and so if this were Archer, I'd probably be able to give you more definitive answers. In ARCHER2, we don't quite understand where the bottlenecks are, and there are 2 network interfaces per. ARCHER2 is more balanced than Archer. Archer had 2 physical CPUs per node and only 1 network connection. So actually, one of the CPUs had privileged access to the network. The other one was a bit off to the side. On ARCHER2, we have 2 64-core CPUs per node and 2 network interfaces. So it's more balanced in that sense. But I have seen effects like you're saying, and I have not yet been able to bottom out whether it's other people. I've been on holiday recently, actually, but so with one code I get the same for 100 input on 64 output. Okay, so that's, I mean, it would be very interesting to look at that to try and understand what the bottlenecks are. I mean, that can be the other thing that could be is memory bandwidth. That's a standard reason for programs not scaling within a node, is that a shared memory node has a limited amount of memory bandwidth. And basically, if you're 64 CPU core, so the 2 questions are: is that a communication limitation or a calculation stroke memory bandwidth limitation? And secondly, if it's communication, is it bandwidth or latency that's the issue? So yeah, okay, that's very interesting. So again, what I would say is, what a lot of people were doing a decade or so ago was they had situations like yours. Said, "Oh, I think adding OpenMP would help me, but it takes a lot of effort, which I'm going to actually cover now." And then they didn't get any benefits. So, and the other problem, of course, this is architecture specific. Once you start talking about performance, yeah. So Rajesh says many CFD codes are usually memory bandwidth limited. As far as I know, yes. So exactly. I mean, one of my standard test examples is a very simple CFD code, and I mean, the reason that we have a small amount of memory per CPU core is that what's happening is that people are just sticking huge amounts of CPU cores onto nodes, many more CPU cores than the memory can possibly cope with in terms of capacity, but also in terms of bandwidth. And so, modern computers are screamingly fast for calculation, but woefully poor in terms of reading and writing data to memory, unless it fits in cache. Yeah. So yeah, in terms of local performance, then efficiently using the cache is the only thing you can do. Well, is the key technique. Okay. So I'll go through this 10 minutes. So development maintenance will be harder than for pure MPI code. OpenMP Pro is easier than MPI, but it's still parallel programming and it's quite hard. OpenMP has subtle race conditions and non-deterministic bugs. It's very rare in MPI to have subtle. The only time you get subtle bugs in MPI is when you issue a non-blocking communication on an array and mess around with that array, read write it before you complete the communication. So you have a race condition there. You don't know if the communication is completed before or after you alter the data. However, that's quite rare in MPI, and it doesn't actually happen in practice a lot. OpenMP is fundamentally built on threads reading and writing to the same data at the same time. Therefore, it's up to the programmer to make sure that there aren't any race conditions. And it's, just because your code runs correctly doesn't mean it's right. It's very, very good. Oh, so Kevin are you saying you had a subtle MPI bug yesterday? Okay, yeah, it does happen. But typically it's localized. Typically you're looking at a function which starts the non-blocking communications, does some stuff and finishes them. And if you've got that wrong, you're kind of looking at all the code that there is to look at. The problem with OpenMP is that it's much more global. But yes, it does happen, Kevin, absolutely. Portability, OpenMP and MPI are highly portable but not perfect, but combined OpenMP and MPI and OpenMP is less so. And the main issue is thread safety of MPI. So in the next lecture, we'll talk about the different ways of doing MPI plus OpenMP in practice, but the simplest way actually just uses the serial MPI library, but the most complicated way requires the MPI library to be thread safe. In other words, to be able to be called by multiple threads at once from the same process. MPI was not designed to be thread safe, and so it's kind of been hacked on afterwards. So if you require that maximum thread safety, portability will be reduced, because some MPI implementations will not support it. They will say, sorry, I can't do that. It's less true now, but it is an issue. And also, it is very desirable to make sure your code functions correctly as a standalone MPI code, so you can get rid of take out the OpenMP. As a standalone OpenMP code is a bit harder, possibly, but definitely as a standalone MPI code. So, whoops. Sorry, I'm hitting too many buttons here. Sorry. So I've done portability or libraries. Yeah. So if the pure MPI code uses distributed memory library like an FFT, you might need to replace it with a hybrid version. Again, if you have a sequence, if you use the main thing here is that if you use library calls, okay, within your program, FFT libraries, blars, blacks, all these things, you have to be careful, because you could have two. Now remember, when you run hybrid MPI plus OpenMP, you are running fewer MPI processes than physical cores. So we'll say we have 128 CPU cores on ARCHER2, we might run 16 MPI processes, but each of those will have 8 threads, giving us a full 128 CPU cores. The problem is, if you call a library from MPI, it might not be threaded, in which case you're unsubscribing the library. Or worse than that, if you call it in a threaded version, the library may create its own threads. You end up with too many. So that, if you're using libraries, it does become quite difficult. Again, there's performance pitfalls. OpenMP can add additional overheads not present in the MPI code, synchronization, false sharing, which is a cache effect, and NUMA effects. I mean, the main problem is that if you think of an ARCHER2 node, it has two 64-core CPUs. Each actually, although it looks like a single memory space, in hardware it isn't. And so one of the 64-core CPUs can access the memory of the other one seamlessly, but it's actually slower. There's non-uniform memory access. And actually, in practice, it's very difficult to get OpenMP to scale beyond a single CPU. So you would very rarely expect to use 128 threads per CPU per an ARCHER node. Sorry, ARCHER2 node, you'd use at most 64. But then you have a tunable parameter, the number of threads per MPI process. And so, you end up having to do a big scan, saying, does hybrid MPI OpenMP benefit me? If so, where's the sweet spot? 64 processes, 2 threads, 32 processes, 4 threads, and then where do they go? Okay, placement of MPI process and associated OpenMP threads can have performance consequences. And again, neither MPI nor OpenMP say anything about that. It's controlled by your job launcher, and I actually have an exercise where you can play around with that. And so you may have written the world's best hybrid MPI OpenMP code and given it to a user. If they aren't careful in the way that they deploy that, then they're not going to get good performance. And this is the biggest thing. This is, I think it's obvious, but it isn't obvious. If imagine I had 6 CPU cores, I ran an MPI code, okay? All the way through this program, yeah, all these CPU cores are running an MPI process. They're all running 100%, okay? When you run MPI plus OpenMP, let's say we're going to run one MPI process, but then have 6 threads. The important point is when you launch the MPI process, you are only running on one of these CPU cores. These are idle. So these are only used in parallel regions when you spawn the threads. Now, OpenMP is an incremental approach. You can choose not to parallelize this loop and only parallelize this one. But every part of your code which doesn't use OpenMP is running on fewer MPI processes than physical cores. You're wasting resources. And so although you may have a code where the central computational kernel will benefit from hybrid MPI OpenMP, but the rest is perfectly happy in MPI. If you want to write an MPI plus OpenMP version, you have to put MPI plus OpenMP into the whole code, because it isn't that these 6 MPI processes magically become threads. The important point is right from the outset, if you run a hybrid MPI OpenMP code, you are running fewer MPI processes than CPU cores, and so you have to put OpenMP in everywhere. It's Amdahl's law inside the node. And so what happens is, okay, there's more pitfalls. I'm running over time. There's a lot of issues here. You might need more synchronization. You need OpenMP uses global synchronization within a node, and it's harder to overlap your OpenMP and with your MPI, and OpenMP codes can suffer from false sharing. This is a cache effect, and actually, cache thrashing happens when 2 threads access the same data, and so it accesses some data, takes a copy in its cache. If another thread accesses the same data, then my cache is invalidated, and it's updating the other cache, and you just spend all your time updating your caches. And that is that's called false sharing or cache thrashing. And it doesn't lead to an incorrect code, but it does lead to very poor performance. I should have said this maybe at the start, but one of the reasons why MPI programs work remarkably well on shared memory nodes is that by definition, in MPI, you cannot directly access anyone else's memory. And so MPI codes are perfectly cache friendly. They're 100% cache friendly, because by definition, my process cannot access the data for another process. And so that's actually, it's not why MPI was designed the way it is, but people often say, surely if I'm running on a shared memory node, I should use OpenMP, not MPI. Well, bizarrely, although it doesn't take advantage of the shared memory nature of the node, MPI programs run very well on shared memory multiprocessors. The NUMA effects I've talked about. Nodes which have multiple sockets are non-uniform memory access. Each socket, each CPU has its own block of RAM. Okay, and this is the operating system has to allocate pages to physical memory. And so when you get some memory, the operating system has to decide, do I allocate it on CPU 1 or CPU 2? In Linux, it often uses first touch policy. Basically, it's allocated where it's first used. This can often be really, really bad. And so, again, NUMA effects can limit the scalability of OpenMP. So actually, it tends to be the case that typically you run one MPI process per NUMA domain rather than one MPI process per node. And actually, even the 64 core processors on ARCHER2 have a substructure where there are actually 4 16 core mini processors. So actually, on ARCHER2, one would guess that the optimal thing to do is to run 8 MPI processes per node, ensure the first 4 are on the first CPU, the second 4 on the second CPU, and then have each of them launch 16 threads. But that's a matter of experimentation. And we have an example to show how you can at least ensure that they're placed correctly. And the process thread placement, we need to make sure that the MPI processes are spread out across the sockets properly, and the OpenMP threads are on the same, are tied to their parent process. Not all back systems do a good job of this, and hyper-threading makes it even more complicated. But I mean, Slurm is a lot better than it used to be, and on ARCHER2 it's reconfigured reasonably well. So that's the first, just about on time, the first lecture where I've talked about the general issues, and what we're going to go into the second half of the lecture is actually look at how you do actual MPI plus OpenMP programming. But I'm going to stop there for the first practical session. But I just wondered if there were any questions on that. Feel free to use the audio if you want. Seems to be working reasonably well today. So the exercise, I'll maybe spend 5 minutes just describing the exercise because it's slightly free form, but hopefully useful to you. So I need to log on to onto ARCHER2. So let's share the right, stop sharing and share the correct window. So there were some problems on ARCHER2 which have been fixed. We were on a different login node yesterday. Okay, that's interesting. We're back on UAN1, so it looks like they fixed those problems. So the exercise is apologies, I have lost my so the code is on the website. If I just I get it, it's just a tar file. If I tar xvf traffic.tar. So what I've done is I have this code which is a traffic model, very simple traffic model, and I have given you an awful lot of versions of it. In fact, I've given you too many, but there is a serial version of the traffic model in C and Fortran. There is an OpenMP version in C and Fortran, an MPI version. There isn't actually a hybrid version, there's just dummy, there's a few. So the idea of the exercise is to basically understand this traffic model where I have given you an MPI and an OpenMP version and combine them to get a hybrid version. Now, I haven't told you how to do that in MPI plus OpenMP yet, but the idea of this first practical session is just to get to grips with the code. So if I show you the source, not the source code, the exercise sheet. The exercise sheet is basically well, I try and share the correct window. It's not working. The share seems to be a bit twitchy. Okay, so there we are now. You know, there's this traffic model code which you can compile and run. I mean, there's a bunch of MPI exercises which you might want to attempt. There's a bunch of OpenMP exercises, and there's a thing about the hybrid MPI OpenMP here. I mean, so you can, I mean, this is comes from a much more from a sort of a larger course. But I thought I'd give you everything so you can work at it. I mean, I would say, you know, maybe if you want to do the exercise, spend your time getting to grips with compiling and running the MPI code, and and just seeing you understand how it works, and compiling and running the OpenMP code, checking you understand how it works. But if you want to work, if you're interested in hybrid MPI OpenMP, the first thing here is process placement. So just had a comment that the audio is cut out. Is that a local thing?
Works for me.
It's okay here.
Right. It must be so that was from okay, Nikki. Okay, it looks like it's just, yeah, okay. Apologies, Nikki. It looks like it's a local thing. In the hybrid directory, the only thing I've given you is a little batch called ARCHER2 job, but it runs a program that I think it's a Cray program called XT-High, and it does nothing but print out where the processes and threads are running, and so that's very, very useful. So that I've given you a batch script there which you can play around with to see how the slurm options, which specify things like the number of processes per node, the number of threads per process, and things like that, how when you change them they alter the actual placement, and how can it go wrong. But then the actual exercise, if you wanted to go, would be to combine the MPI and OpenMP together to get a hybrid traffic. And we'll also use this exercise for the afternoon's lectures as well. If you haven't seen the traffic model before, I'll just show you one slide to explain what it does, and I will go back. I'm slightly. Yes, thanks, Kevin. The reservation is the reservation names are quite logical now. On Archer, they were completely random, but they seem to be actually. So I just give you a. So what the traffic model does is a very, very simple exercise. So what the traffic model does is the cellular automaton model, and we have a road which has a number of cells. I think it's set to a few thousand, and the cells are either occupied or unoccupied. So if the value is 1, they have a car. If the value is 0, there's no car. And we have a series of iterations, and what we do each iteration is cars simply move. If this car can move, this one can't, and this one can. So the only rule is, the update rule for this incredibly simple cellular automaton is that if a car can move, it does. If the cell ahead is empty, you move. If the cell ahead is full, you don't move. And all it does in this case, so these two guys would move. Then, whoops, sorry, these two guys, then this guy can't move, but these two guys can. And actually, when you get to that situation, then they can all move. And the interest in the model is to actually compute the average speed of the cars versus the density of the cars, because you get congestion. So in MPI, you can see the important point here is the state of a cell depends on its two neighbors, and therefore you have halos and halo swapping when you parallelize this. The OpenMP is parallelized differently, and so so yeah, so that's really, that the code is very, very simple. It's really just there as possibly the simplest possible halo swapping code you can imagine. You exchange data with your the process is arranged in a line. This is the MPI code. The process is arranged in a line. You exchange data with your neighbors. But of course, you can also implement this OpenMP. The only other thing to notice, the boundary conditions are cyclic, and so it's like cars on a roundabout. When this car moves here, it reappears back here. So that I've got cyclic boundary conditions, which is just for simplicity. They go back round the way. So that's the exercise. So as I said, the idea is, if you want to do the programming exercises, familiarize yourself with the MPI code, familiarize yourself with the OpenMP code, and then after the next lecture, we'll know enough to actually put them together. And in the after the afternoon's lecture, you'll know enough how to implement it in shared memory using pure MPI on a node. And again, I actually have a solution. I believe I have actually. Oh no, I haven't. I need to put them up. I'm also going to distribute solutions for the MPI shared memory approach, as opposed to hybrid MPI plus OpenMP.